In this video, we'll be discussing some of the techniques and strategies that we need to get started using these inferential statistics that we've been talking about thus far. So, as we saw with normal distributions, statistical distributions, which can be represented in both equation and visual form, are probably most easily considered graphically versus their equation form. Now, I've alluded to thus far in the lecture set that these distributions are directly connected with probabilities. That is, how confident or wrong we want to be, and the probability of that confidence or the probability of being wrong. Now, on the graph, if we're going to look at statistical distributions graphically, probabilities are going to be shown as shaded areas under the graph. So we're going to shade or talk about the area under the curve for particular regions under the curve. And those area under the curve, and again, visually it'll be shown as a shaded region, those are going to be the probabilities. So one shaded region might represent 10% of the area under the curve. One shaded region might represent 80% of the area under the curve, etc. Now, what we're going to look at with these areas under the curve are the distributional values. That's the entries on the x-axis that correspond with those particular probabilities. Now, these can be visualized as vertical lines or cut points as to where the area cuts off. And these will be called sometimes critical values. So let's look at it visually because I feel like it's harder to describe than it is to just see what we're talking about. Now here we'll show three normal distributions. One with 90% of the area under the curve shaded, one with 95% of the area under the curve shaded, and one with 99% of the area under the curve shaded. You can see here that there are two cutoffs, one at negative 1.645 and one at positive 1.645, that indicate the edges of the shaded region if I want the middle 90% to be shaded. So this 90% cutoff, and eventually we'll be using this as 90% confidence, or correspondingly 10% error, is associated with the cutoffs in the standard normal distribution of positive 1.65 on the top and negative 1.65 on the bottom. It's worth noting that we leave room for error on both the top and the bottom. Our guess could either be too low or too high, so we could have error on either side. And this error percentage, if we want to be 90% confident, we'll have 10% of error, is split on both sides because we could be wrong in both directions. So here, our guess could be wrong in either direction. It could be, our sample mean could be below the population value or above the population value. So if we want 90% confidence or 10% error, our 10% error would be split into two, 5% error of the top and 5% error on the bottom. So there's a 5% chance that we overestimate, 5% chance that we underestimate with this graphic. And this is the general rule of thumb, that we split our error in two and put it equally on the top and the bottom, though there are occasional circumstances that we won't cover in this class, at least not within this lecture set, where when making a decision, it doesn't make sense to allow for one or the other, and so we put all the error on just one side. We're going to skip over it in this lecture set, not because it's difficult. In fact, it's relatively easy. We're just not going to discuss it in this course, as it tends to be something that shouldn't be often used. Now, the biggest thing I want you to see here with this standard normal distribution, and it applies to other statistical distributions where we have the equation and they're defined, is that we can connect our percentages of confidence with the values on the distribution. So again, percentage is the shaded area under the curve. And the value on the distribution, the cutoffs are these cuts where we say, okay, you stop shading here at 1.65 positive, you stop shading here at negative 1.65, and if you shade everything in between, you get 90%. So the percentage of our confidence relates directly to values from the distribution. Let me say that one more time. The percentage of confidence relates directly to values of the distribution. You'll see that this is true no matter the confidence. Now, if we have a different percentage of confidence, we'll get different values on the distribution. So for 90% confidence or 10% error, I'll get values on the standard normal distribution, 1.65 and negative 1.65. Incidentally, for symmetric distributions, the normal distribution, the t-distribution, this will always be plus and minus the same number. But for 95% confidence, I'll get a different number on the standard normal distribution. I'll get 1.96. For 99% confidence, I'll get a different number on the standard normal distribution. I'll get 2.58, the plus and minus version. So each percentage corresponds with a number on the standard normal distribution. And again, this is true for any defined distribution with our statistical properties that we look for. Now, the formal way to calculate where these values are for a particular area, so how do I know that 90%, how do I calculate 1.65 from the 90% confidence that I want to have? The way that we get that is calculus. And we're not going to do calculus in this class. Instead, we're going to use computers, which can do that calculation. Now, I previously briefly referenced degrees of freedom. This looks exactly the same with degrees of freedom. We plug in our confidence that we want, maybe from the picture. Here for negative 1.65, this is our left cutoff. We have 5% of the area below it and 95% of the area above it. This 90 plus the 5 on the top. And then vice versa for 1.65. Here we would plug in for normal distribution, give me 90 plus 5, 95% of the area on the left for a normal curve, and I would get 1.65 as my cutoff for that value. Or 90% in the middle, and I'd get two cutoffs, negative 1.65, positive 1.65 in a normal distribution. We can do the same thing with a t-distribution. I just tell it, instead of using the normal, use the t, and I give it that additional piece of information, that degrees of freedom, which is n minus 1. Well, we now have all of the components that we need to do inference. That last piece that we just talked about, that connection between the percentage of confidence versus, percent error, either one, however you want to phrase it, and the distribution, those values from the standard normal distribution, that was kind of the last thing that we needed. We'd kind of been leading up to that over the last couple of videos in this lecture set. And now we can go on and combine all of these different pieces. So real quick, let's identify what these different pieces are. So first of all, we have the best guess from the sample. So for mu, the population, best guess of the population value. So again, our goal is to make a decision for the population, and we're going to guess at that as well as we can. So the best guess of the population, say mean, from the sample is x bar. The population mean is mu. X bar, the sample mean, is our best guess at that. Now, we will call this the point estimate. It is a single point or a single number that is our best guess. All right. The next thing that we need is the variability of this guess. And what do I mean by variability of this guess? Well, recall if I have a single sample, I calculate a single mean, and there's no variability. But if I took a different sample, even of the same size, it's going to have some different people in it, and the mean is going to be slightly different. So what is the variability if I looked at all of the different samples and took all of their means? Recall that distribution is called the sampling distribution. What's the variability of that? Well, that is the variability we're talking about here. We denoted that variability as, or the standard deviation, as sigma sub x bar. We also had sigma squared sub x bar that we defined. And this was just the original standard deviation of the population divided by the square root of the sample size for the size of the samples we're taking to calculate the mean. So we talked about this in a previous video in this lecture set. And for our purposes, when we're combining all the pieces, we'll call this the standard error. And we introduced this terminology earlier. So we have the point estimate. That's our sample mean when we're estimating the mean. We have the standard error. That is the standard deviation of the sampling distribution, which is the standard deviation from the original data divided by the square root of n. And when I say standard deviation of the original data, I really mean look at your data values, whatever they are, calculate the standard deviation. That's this. Well, this is the population value. We would use S or sigma hat to estimate that population value. But that's what I'm talking about with this. And n is literally count up how many data points you have. So these two things are things that we've done before in this class. Very approachable from a calculation standpoint. The last thing that we just talked about is the probability of certainty that we want, or again, inversely, error. So 90% certain, we would be 10% error, 99% certain, we'd have 1% error. And the population cutoffs for this probability. So again, when I say population cutoff, what I'm introducing is the fact that, remember, in the central limit theorem, we said we know how the sampling distribution behaves, and it behaves according to a standard normal distribution. So for the mean. So in this particular case, we use the cutoff values, which we'll call critical values, for the particular probability. So just like before, I have my probability. I plug into the computer my probability, and it spits out my critical values, the positive and negative one. All right, so all that's left is to put these different pieces together. Again, for the mean, we have a couple of different options. One is the hypothesis test, and the other is the confidence interval. Now, there's a couple of distinctions. Hypothesis test is decision-making focused. Confidence interval is a little bit more exploratory, but can also help with decisions. So there's that distinction. But for me, I'm going to talk about it in ways of the calculation. And in terms of the calculation, these are actually very similar, but they go in different directions. In a hypothesis test, we put the data on the scale of the distribution. So we take our standard normal distribution, mean of 0, standard deviation of 1, and we put our data on that graph. Now, in a confidence interval, we take that graph and we transform that graph to be in terms of our data. So for the hypothesis test, I'll call it putting our data on the scale of the distribution. And for the confidence interval, I'll describe it as putting our distribution on the scale of the data. So we're putting them on different scales. Again, hypothesis test, we start with our data on whatever scale it is. So if I'm doing age, it's age in years, and that's the scale we start with. And then we move to the central limit theorem, or we use the central limit theorem form to transform the what we start with, our sample mean on the scale of our original data, and we use this standardization formula and the central limit theorem. Recall the central limit theorem said that this first quantity right here is distributed as a standard normal distribution. So central limit theorem form says this value right here is distributed as a standard normal. Now this value is our point estimate, mu, minus the hypothesized population mean, which we'll talk about in a moment, divided by all of this stuff on the bottom, which turns out to be the standard error. Recall this was sigma sub x bar, the standard deviation of the sampling distribution, and that is our standard error. So standard error equals sigma divided by the square root of n. Or sigma sub x bar, which is sigma divided by the square root of n. So this first value, x bar minus mu divided by sigma over the square root of n, this first expression is sometimes called the test statistic. That is, what does our data value look like when it's put on the scale of the standard normal distribution? And so we're going to compare this with the critical values from the distribution calculated for our confidence percentage. So we're going to have the confidence percentage. We're going to plug it in the computer, and we're not going to get a graph like what I showed earlier because that's a little bit overkill, but we will get the cutoffs from that graph. And then we're going to compare this value, our data on the standard normal distribution, with the cutoffs from that graph. And we'll talk more about that in a second. Now, the confidence interval is going to start at the same place, but it's going to work the equation from the central limit theorem backwards. So it starts with the same equation, that is this test statistic equals a value on the standard normal distribution, this kind of critical value. And now, instead of being on the scale of the critical value, we're going to solve to figure out what mu is in relationship to all of this. And if we work this out, and if we have both the positive and the negative critical values, then we get this expression, which is the general expression of a confidence interval. Ultimately, this puts the critical values or the cut points for our confidence percentage on the scale of the data that we're working with. So we would start with, negative 1.65 or whatever we had, and positive 1.65. And then we would put that on the scale of age in years. Now, our goal is that the population mean will be in this interval with a certain degree of confidence. So we'd be 90% confident or 95% confident. And those different confidences would give different critical values that we would put into this equation. But for that level of confidence, we'd plug in those critical values. And then we are that level confident that the population mean will be in this interval. And again, this is calculated using the positive and negative critical values. That's this plus minus, is both the plus and the minus. So this gives two numbers, just like in our critical values, we have two numbers. We had a top a cut for shading on the, stop shading here on the top side, and then a cut on the bottom side, stop shading here on the bottom side. We have the same thing with this formula. The plus gives the top cutoff, and the minus gives the bottom cutoff. Now, it's an important reminder, and I'll repeat it until I'm blue in the face and you're sick of hearing it. Mu, that U with a little flag in front, is the population value that we don't know. We're trying to make a decision about it. The only thing that we know is this X bar and other estimates from the data. So we'll know N from the data. We'll make an estimate of the standard deviation from the data. But we don't know this mu, this thing we're trying to make a decision about for the population. So we're trying to use X bar, knowing that X bar is wrong, along with our guess of how variable X bar is, this standard error, to put together a reasonable range that the mu would be in for the confidence interval, this population value would be in, or to make a decision regarding mu with a reasonable degree of confidence in the hypothesis test. That's the goal. One question sometimes I'm asked by students after going through some of this stuff is, why do I calculate a confidence interval for the mean when I already calculated the mean? And it's a good question, but again, it highlights the point I'm trying to make here. We know the sample mean. I know the mean of the patients who've been in my hospital for the last 30 days, or I know how successful the medical procedure was in my couple of test hospitals. What I'm really curious about is, how well is this going to work more broadly? How well is improving my ED intake procedure going to save my staff time at all of the hospitals? And I'm trying to make either a guess about the average amount of time saved or a decision about if it actually saved time or not for the population values, not the sample that I studied. That's why this is necessary and useful. We can assume that this is a perfect representation of the population, that the sample we studied perfectly represents the population, but frankly, that's simply untrue. Even if it's a perfectly representative sample, as we discussed earlier, samples randomly vary. So if I took a perfectly representative sample of 100 people, it's going to be different than a perfectly representative sample of a different 100 people if I randomly sampled 100 people. There's just different people, and so it's going to vary somewhat. And because of that variance, we don't know if it's just varied a little bit further away from the population mean or if it's varied such that it looks like the program was effective. So looks like we saved time in the emergency department intake procedure. How do I know if it really did or if that was just a sample with a little bit lower intake times after we implemented the procedure? And the answer is we don't at face value. This whole process is to attach some confident percentages to my guess at how much time was saved and my guess as to the decision as to whether or not it helped, and to make the process more formal, again, because we know that this isn't exact and we know that this does vary from sample to sample, and we know it's not a perfect estimate of that population value. So we're taking this process is to take all of that information into account to make either a good decision or, again, come up with a reasonable range as to, in this hypothetical example, how much time was saved. In the next video, we're going to jump right into hypothesis testing, showing all of the different pieces of the procedure, as well as ending with a couple examples as to how we can utilize this in practice.